name itself, it says waiting for visa, whatever. So people will come there.
Streaming.
I think generally starts YouTube.
Yeah, when we start, yes, that's right. No, I just said, I mean, it looks like it was not. Yeah, now people are there. People will slowly join.
So normally, if somebody raises hand, do you interrupt? I'm okay with that also, but just asking during the talk.
Right. Normally, we ask them not to, but if there are a small number of people today, there isn't a huge crowd, so we can do that. Yeah. I mean, if you don't mind.
Sure, I have no problem at all.
Yeah.
You just stop and let me know. I mean, I will not keep that because that provision is also there, but it covers my screen. So I will minimize that, yeah.
Nini, so what I will do, I'll keep an eye on this. You don't need to.
Perfect.
I will keep an eye, and I will interrupt and I have them ask questions. Okay, so let's start off. We are again at 4 o'clock on Thursday, and I hope I'm visible. And thank you very much for attending. I mean, we've been doing this for about 3 months now, and you can see how long we've been doing it. It's the length of my hair. That is in the last 3 months since the lockdown started. We have every Thursday brought you a lovely colloquium. And as a result of us going on Zoom and opening this up, and also on YouTube Live, we've managed to have the IUCAA Colloquium reach a much larger audience than it normally does. And that's very gratifying for us. Also, we've had speakers from all over the world and from all over India who would normally be so busy that they wouldn't be able to come and give us a talk here. And there you are, the director of ARIES, Nianital, who is one of the busiest people in astronomy, can just from his office or room or whatever, give you a talk here. This is wonderful. Dipankar, of course, is very well known to many of us. He did his PhD in IUCAA, was the Siraj Hassan, and then spent some really unusual years in his postdoctoral years, as he was just telling me, at Arma Observatory in Northern Ireland. Not many people actually go there to do astrophysics PhDs from India, and then at Leuven, in Leuven in Belgium, and then came back as faculty at the IUCAA Bangalore, and from last December he has been the director of the Aryabhatta Institute in Nianital, which actually has the largest telescopes in India operating under it. But Dipankar is going to talk to us about an amazing work on the sun. And I'm really looking forward to this because in the title we have using Kodaikanal Digitized archives. And this is data that is absolutely amazing. And I'm very proud that IUCAA has been involved in helping get the archive digitized and all the data together. And we hand you over to Dipankar for his talk. Thank you.
Thank you, Shomak, for your kind introduction. It's been a pleasure to get this platform to reach out to more people. And as you pointed out, it's quite tough to travel these days. So this is a new normal. And I think we are able to utilize this, quite efficiently. But it's a new exercise also to really communicate to the individuals. I always prefer to have a face-to-face, looking at the eye and then realize how much it is really transmitting. But that provision is not there in this media. But I will try my best to reach you out. So today I'm going to talk about a long-term study of the sun, why it is important, a little bit of history, and in that particular subject area, how our own observatory in Kodaikanal is really helping out the international community. So this is one of the oldest observatories in the world, and probably one of the oldest archive as well. So this has been recently digitized and made available to the public. There is an animation which is going on in the background. That's a sort of summary of my talk, but I will come back to it much later. So as it was it was mentioned, right now I'm Aries. My roots are still there in Bangalore in IIA, and I'm also affiliated faculty in Center for Space Science Institute in IUCAA, Kolkata. So let me get into the talk. So first I have to tell you where I am. So Aries has two campuses. One in the top panel is the Manora Peak, which is 10 kilometers south of Nainital city. And I am actually right now somewhere here. And we have a more new modern campus in Devasthal, which is 50 kilometers east of Nainital city. It takes about 2 hours to reach there. And that hosts the largest nighttime telescope facility in the country and this part of the globe also. This is a more closer view of beautiful Manora Peak. This is, they also host quite a few, old telescopes, and the students are all hosted here. I'm also, all out here, and I'm right now in this particular room here. If you could see my cursor sitting and trying to reach you all out here. So it's a beautiful campus. Yeah, but most of you are welcome anytime, but of course, when it is allowed, and you see the planes in the background. So today's talk is on this subject called the solar cycle. So what is plotted here is the recorded yearly sunspot number for the last, say, about 400 years. What it shows that, you have the sunspot number varies with time. A typical periodicity of the order of, roughly 11 years, you see it. So there is alternate peaks of solar activity. Sometimes you have many sunspots, which are called maxima. And then there are periods over which you have only very few, sunspots. They are called the minima. So this predominantly cyclic period has a rough periodicity of 11 years. This was actually discovered by Samuel Swabe. And Swabe's observation started in this period, which is denoted here by two vertical black lines. And that's how often also it is called a Swabe cycle. But then there were also very interesting aspects observed that in the past, between 1650 to 1700, there were hardly any sunspots recorded. And there were severe effects of this on our climate. Europe was frozen for almost 30 years. It was extremely cold. The river Volga was frozen for 30, 40 years, and several thousands of people died and so on and so forth. So there was a direct impact of not having sunspot on the surface of the sun. But then, since these observations are recorded, not with very high sophisticated instruments or telescope, we still do not know whether there were spots of maybe very small sizes which were not able to be recorded. Is it possible that Dynamo is a sort of process which is now believed to be responsible for this solar cycle, which I will come to later on? So it is very difficult to stop that. So is it that during that period somebody sort of forgot to cycle anymore, so that you don't get the dynamo in action, or the dynamo was working in a very inefficient way and so on? So this is still a very open and unknown question. So let's now focus on what are sunspots. Sunspots are associated with regions of strong magnetic field. So here is an image taken from a Japanese satellite called Hinode, and you see on the surface. So this is taken again in a white light image, and this is actually in the G band, which is very similar to that. And you see a pair of sunspots. And the other thing what you see is that when you try to get a magnetic information associated with this image, you see additional information that there are these strong fields, and there are also certain flows, which is denoted by these arrows. And these regions are commonly known as active region. But what is to be noted here is this, sunspot pair seems to have a tilt, and this blue line gives that tilt angle with reference to this equatorial line. So always the sunspot appears as pairs, and they seem to have a tilt, which also varies with time. Now that was a close-up of the sunspots. But now if I look at the overall distribution of magnetic field on the surface of the sun, we see these, active region where you could see, pairs of such sunspots dominantly, but you also see lots of small magnetic field, like almost like a salt and paper, distributed all over. What I was referring to this, tilt angle, that also shows a property that this tilt increases with latitude. And the other important aspect is, so that if you go look at a northern hemisphere, you see this yellow polarity, which corresponds to one polarity of this bipolarity, is on the right side of the blue guys. Whereas if you go to the southern hemisphere, the blue fellows are on the right side of the yellow fellows. So there seems to be a opposite polarity orientation in the two hemispheres as well. Why I'm showing some of these general properties of the magnetic field of the sun is because we need to have a theory which can explain all these different properties. So I'm just going through one by one to get a repository what really we need to explain. So what you see here is that, and what is the current understanding about the solar magnetic cycle. This is again an animation produced by David Hathaway from observations from Doppler image and magnetic field measurements on a SOHO spacecraft. So the magnetic field erupts. So let me pause this thing for a while, and then I will explain. So there seems to be two bands of, on the either side of the hemisphere, you see this magnetic field. Here you see one band in the northern hemisphere. And as you said, as I already pointed out, the yellow guy is in the right side of the blue fellows. And then if you go to the southern hemisphere, this is the opposite polarity information. What we do observe is only one face of the sun. We don't know really what is happening at the back side of the sun. To sort of circumvent then, often what we do is the sun also rotates around its own axis, and it takes about 27 days. Oops, let me go back to the animation again and play it. So we try to create a two-dimensional image which depicts the distribution of the sunspots on the solar surface for all these 27 days. That is what it is happening. Now it's like, you are just, creating a 2D map of one full rotation. So that one full rotation corresponds to, it's called one Carrington rotation. And now if I run through these 27 days for many years, starting from 1980 to 2010, what you see is this is a period over which, so over which you will find that there are less number of sunspots, and the sunspots pair seems to slowly moving more towards the equator. And if I just run through again and stop it, so this is a solar minima period, you hardly see any sunspots at all. And then if I just again run it, so it is going into the progressive active phase, and you see lots of pairs of sunspots. They first appear in the higher latitude, and then they go towards the equator, and then they disappear with the solar during the solar minima period. Again, a new cycle is emerging, and you see lots of these sunspots pair and their movements and so on and so forth. So we need a theory which can explain all these, different aspects. So this particular, one map, collecting it or stitching it next to each other, what we produce is, this is called a butterfly diagram. So this is a magnetic butterfly diagram, which runs for the period of, say, roughly 1975 to 2010, because this is a period over which we have direct continuous magnetic field observations on the sun. Before that, we actually do not have a systematic magnetic field measurements on the sun at all. So that again makes the life very difficult for knowing about the history of the magnetic cycles. So here, what the important thing to be noted here, there is equatorward migration of active regions. So active region appear at certain latitude, and then they, with the progression of the solar cycle, they move to the equator. Whereas you will see that these active regions also diffuse, and the weaker magnetic field, after they become weak, they move more towards the pole. What happens is the sun can be also considered as a dipole. So the polarity of the one hemisphere could be blue, and the opposite hemisphere will be yellow in the polar region. But then what happens is this particular diffuse field, it moves to the polar region, and then slowly it eats up the earlier polarity. And there is also a polar field reversal at the maximum of the cycle. So this is again another important aspect which we have to explain by whatever theory we have, that it's just not the distribution of the bipolarity over the different latitude band. The entire sun reverses its polarity almost every 11 years. So essentially, the solar cycle is actually not a 11-year cycle, but it is a 22-year cycle. So that also has to be explained. So now let me give you a little bit of theoretical understanding what we have today. What we sort of, in a global fashion, we try to understand this by a global model of the magnetic field configuration. We start with a poloidal field. So you have a north-south oriented field, and then sun rotates, around its own axis. But also there is an interesting aspect: sun rotates differentially. Basically, the equator rotates much faster than the pole, and that makes life much, much more difficult than a standard rigid body motion. So poloidal field has to actually give rise to toroidal field, and probably eventually toroidal field has to give back this poloidal field. How it is happened? So this is again a pictorial representations of that you start with a poloidal field, and as I was showing, because of the differential rotations, these aligned field that is wrapped around, and then it generates the toroidal field in the form of a sunspot. It comes to the solar surface and it generates these kind of active regions. And as I was also trying to explain earlier, you see these active regions have these kind of polarities where the negative poles are this way, moves upward with the progression of the solar cycle. The positive guys will go to the equator side, and then they will meet the negative fellows coming from the other hemisphere, and they will cancel each other. That's how the solar minima is depicted. Whereas these minus fellows, they're moving to the poles. The pre-existing polarity in the pole side, in the north pole, was plus. So obviously these negative guys will slowly eat up these positive fellows, and eventually the polarity reversal will happen. So there are also some other small little elements which is necessary for this dynamo to work.
Right. His feet stopped?
We lost Dipankar somehow.
So I was first wondering it was me, but he's come back. He's dropped out.
Yes.
Let's see if he comes back. I'll call him.
He's back, it seems. He's back.
Yes, he's back. Dipankar?
Yeah, can you hear me now?
Yeah, we lost you suddenly. Yeah, we can hear you.
Can somebody confirm that you can hear me now?
Yeah, we can hear you.
Yes, we can hear you. We can hear you.
Hear us, I think. I'll call him. I think.
Are you able to hear me now? I mean,
yes, we can hear you.
There was
yeah, we can hear you. You can't hear us.
Data drop, and we lost for a few
I
minutes.
think he cannot hear us.
Yeah, I will. I am calling him on the phone.
Okay.
Hello? Yeah, we can hear you, but you can't hear us, it looks.
Okay, fine. Okay, I will continue then.
Okay.
Okay, yeah.
Thanks.
Okay, I muted myself by my speaker probably. That's why. Sorry about that. Sorry. Okay.
Right.
So how many minutes you lost? I mean, is it?
It's all right. Don't worry. We go ahead.
Just go ahead from. You were talking about the dynamo.
Right. It has to continue. Okay, so what I was just referring to, that this poloidal field, gives rise to the toroidal field through this differential rotation, and the toroidal field, the emergence and decay of the active region, these pairs are drawn by this meridional flow to the polar side. So how do you parameterize these meridional flow and turbulent diffusivity and so on dictates the different time scales. So basically, we have two kinds of field which we have to worry about. One is this active region field, which is called the toroidal field. And the top panel shows the variation of the toroidal field or the sunspots in the two hemispheres. But then, as I mentioned, the directly magnetic field measurements are not there in the past 100 years or longer. So what we do is we try to get proxies. So we assume that if the sunspots are having larger area, of course it will represent some way the magnetic flux, and that can be a good proxy for the quantification of the magnetic activity of the sun. So here what is shown here is the sunspot area on the top panel, and in the lower panel it is showing the poloidal field, which I indicated. So what is to be noted here is during the maxima you have the polar field to be minimum, and when the toroidal field is minimum, then you have the poloidal field as maxima. So that's the polarity reversal which happens. So again, here there is a sort of dynamo current flux transport dynamo model, their simulation output. This is again one of our colleagues from either Kolkata, Dipendu Nandi, has led this team to come to this kind of understanding of the solar cycle. So the magnetic field is generated at the base of the convection zone. It pops up into the active region, then it is drawn to the strong ones is drawn to the equator, and the weaker ones are drawn to the polar side, and then you start the next cycle, and so on and so forth. So that's the current feature of the understanding of the magnetic cycle. Now I will come to the Kodaikanal data. So this is hosted in this particular website. This is a unique archive, because also it has a multi-wavelength aspect which is not there in majority of the 58, if you go to the archive, you will see one image in white light, one in calcium, one in H alpha, and one a sort of almost like a chronographic image as well, blocking the solar disk and taking some calcium images to capture the prominences. So this data exists from 1904 to 2007. After that, this particular instrument was stopped, but we have another telescope, and I will talk about later on how to talk about the continuity and so on and so forth. And in that case, Aditya's one of the payload suit will actually provide us a natural continuity of some of the science which I have been projecting here to do it, as a continuation. So this is Kodaikanal Observatory, and you see this building in the top. We have a small little seminar room here. We conduct a lot of lecture series here. This is the small little telescope at the top of this, pillar you see is taking this images of the sun with a white light, filter for last more than 100 years. In fact, even today, if the sky is clear, one boy has gone up to the this place and taken one image with a X-ray film. It is just for archival and historical purpose. We are continuing this observation because the modern day people take CCD images and so on. But just for the continuity sake, we are still continuing taking one image every day. It's a huge archive, and we have digitized it. I will not get into too much of details in terms of the process of digitization or the calibration, but if somebody is interested, I can answer questions later on, or you can contact me later on as well. I will be happy to answer, and if you're interested in the data, we can give you all the processing techniques and all that. Basically, one should note that there are a lot of calibrations which is needed, because as you can imagine, this data has been there for 100 years, so there are lots of dirt and other elements, could be even fungus, which you could identify as a sunspot as well. So one has to be very, very careful on that. But thankfully, I got very bright students, and they have implemented a lot of automated methods, including sophisticated, and now we are moving into even AI to use this data. So again, this is a source of a big data. We have 20-30 terabytes of data for you to play around. So if people are interested to work with the big data, this is again another huge source. So through this automated method, we identify these places where there have been sunspots, and we measure the sunspot area. And all these locations of the, of the sunspots, their latitude, longitude, area, the time, all these informations are in the public domain now. And there are a lot of people working with this. So this was our first result from the Kodaikanal data. What you see here in the top panel is the sunspot area as as it varies with time. And we had to compare with a Greenwich because that's almost like a standard candle for us. It has collected data from all across the globe, and they created a series. So your always verification of your results are done often with the Greenwich data, and we find reasonably good match. What we did, which earlier people were not doing, was also to look at different sizes of sunspots. So here in the lower panel, what you see is this butterfly diagram, which I have told earlier. But now we are also providing another information, bringing in the sizes of the sunspot. The question is, biggest sunspots are depicted by the red ones, the green ones, and progressively smaller and smaller size. So what is to be noted here is the biggest guys are only coming during the maximum time. And they seem to also, restrict themselves to some more lower latitudes and so on and so forth. Whereas the smaller guys can actually come in very different latitude bands and can have different phases of the solar cycle. So this is again deals with the question of the formation of the sunspot, how the sunspots are formed, and their size distribution, whether that has any physics behind it as well. This is the current state of this data. This is done by my former student who is now in Max Planck Institute in Germany. And what he has done is he has cross-calibrated sunspot area across 13 observatories across the globe. So this was actually my dream 3 or 4 years back when we started looking at the Kodaikanal data. You see, when you have a time series from one particular observatory, it will have its own challenges. It will have data gaps. It can be affected by weather. It can be also affected by instruments. So this cross-calibration of your data, similar kind of data across different observatories across the globe, is the way forward. And unless you do that, you cannot make a composite series. So I think this is just been accepted in astronomy and astrophysics, will be appearing probably in next month. And this is the state of the current understanding. And then following our particular emphasis on the different area, we have produced these kind of butterfly diagram and this solar cycle feature also. There are many other features also which needs explanation. As I pointed out, that sun is not symmetric. The northern hemisphere and the southern hemisphere doesn't really behave always in the same way. What is plotted here, this is also called, you can measure or sort of quantify this asymmetry by different methods, different formulas. Whatever it is, you always find that there is a north-south asymmetry. And this north-south asymmetry also need to be explained by a standard dynamo or whatever theory. Long-term study of the sun or old kind of data. I've been always, known as a space person. So,
Dipankar, I'm switching off your video because your voice is cutting up. Okay, or you can switch off the video. Okay, but go ahead.
Video is switched off. Okay.
Yeah, I switched off the video because there seems to be some bandwidth problem. So we'll bring you back again later on. But just carry on. We can hear you.
Sure. Thank you. So, what is important here is that to collaborate with a number of people. So I have not been involved with the Dynamo models and so on and so forth. So now what I'm trying to do is, this is a group from Russia. They have been working on this long-term study and the Dynamo models and a different aspect. Of course, within in India also we have very sophisticated program led by Professor Aryabhatta and his students. So I'm collaborating with them as well on a different aspect of the kinematic dynamo model. So I'm just trying to utilize my data and interact with very different theory groups who are all trying to explain the same phenomena. So I provide new observational constraint from looking at these kind of archives. and put this challenge to my theoretical friends, and we are coming up with some solutions in some aspect. The other thing which we also pointed out is that this different sizes again. What I have plotted here is the sunspot area. If you do not make any distinction between a big one and a small one, this is how the sunspot cycle looks like. And as I said, as you can see, this is the cycle 19, which happened between 1957 as a peak time. This is the strongest cycle for last 100 years. We still do not understand many features of this 19th cycle. But now, if I just take the smallest sunspots into consideration, what I notice here, these are the smaller bin sunspot sizes. It's not the 19th cycle which turns out to be the strongest. It is actually the 21st cycle which turns out to be the biggest. So this is a peculiar thing which we are observing. Is it that the small sunspots and the big sunspot, they're all generated by the same mechanism? Is it possible that the smaller guys are born from the bigger fellows by fragmentation, or the other way around? The smaller guys come together and make a bigger size. So these kind of questions actually also shed light on this entire mechanism of the sunspot formation itself. So these are some of the constraints I'm saying, we are trying to project from the data what we have. So this is my purpose. Then there is again another interesting aspect. You see, during the peak phase of any solar cycle, this is called a double peak. It appears that, whatever number, sunspot area, sunspot number you look at, the number goes up, then it drops, and then again it goes up again. So this is called the double peak of the solar cycle, and the normal solar dynamo theory was not able to explain this. So this is the work which I did with Vidya Karak, who is now a faculty in IIT BHU, who was again Arnab student. Most of us are actually some way connected with Arnab. But this is again an example that how some of our data, we are trying to get a physical explanation by collaborating with theoreticians within the country as well. This is probably a bit bigger explanation. I will skip this because I may run out of little time. So this is the summary of the white light data, which only looks at the solar surface. And till now, we have quite a few publications from this and different aspects of this sunspot area series. There is something also called Waldemar effect, that the rate at which the solar cycle grows and the decay rate is different. So there are certain features. In fact, there is another feature. There is a preference of sunspots to appear in certain longitudes even. We only talked about the different latitude band and then the progressions of the sunspot with the solar cycle. But it appears now that there is also a preference in active longitude. In fact, there are a lot of interest in this particular subject area, but it's quite a tough things to, because we don't see the backside of the sun at all. So it becomes quite a bit of challenge to build this. But you have projected something on that. And as I mentioned, the double peak of the solar cycle, I did not talk about the sunspot details in the sense sunspots has a core, which is called the umbra. And then the periphery of that sunspot is called the penumbra, where magnetic fields are actually more horizontal. In the core, the sunspots are more vertical. So there are lots of physics behind this. So one of my current PhD students is working on that and this asymmetry and so on. So there are many different problems. I won't have time to go through everyone, but I thought I will just impress on you that this is an old archive. Often, probably 10 years back, people will say, "Oh, these old data are not useful for anything." But I think this is a gold mine now, and the international community have started using it. And this is, I just wanted to emphasize that this is in our own backyard. I will talk about now the next layer of the atmosphere of the sun, which is recorded by this calcium K line. And we have this record again for last 100 years. This has been digitized with this 4K by 4K SSD. This is the data volume. This is again one of the longest data volume. Interestingly, I want to also emphasize a few points that you see the data availability reduces after 1980. Often we think the older the period you go, you will have problems with the old data, their quality and all that. It's just the opposite. somehow, I don't know, it's a mixture of many things. Either the earlier observers were very good, or they preserved the photographic plates or films way. Of course, the environment also has to be blamed. Kodaikanal atmosphere has been actually spoiled by more people coming in, hotels and so on. So what we see very, very clearly that beyond 1980s, there is a drastic change in the quality of the images. So this is quite amazing that the older data quality up to 1960s, 70s is so much better than the current last 30 years or so. So this is again, I will not go into the details of how you do the data calibrations and so on and so forth. But a similar example I am showing you here, as we were doing the Carrington map of the 27-day, the location of the sunspot on the solar surface. It's a similar way you can do this Carrington map for calcium. And what you see here is these patches, they correspond to, again, active region. In calcium, when you see it, they are called plages. So the plages, again, represent the location of the magnetic field underneath, because the calcium is formed at an atmosphere roughly, say 1500 kilometers above the photosphere. So you see how the magnetic field is connected from different layers in the solar atmosphere. And this, again, a direct manifestation or proof that wherever you have sunspots, you really have a bright emission on the higher atmosphere of the sun. And this emission actually brings lots of information about the total solar luminosity. Is it the total solar luminosity of the star is constant? Of course, for all practical astrophysical context, we consider solar luminosity to be constant. But now we see that there is a 0.1% variation of the solar luminosity with solar cycle. And this, if from this 0.1, this variation becomes higher, then we are in trouble, actually. It will affect our climate and so on and so forth. So it has a long-term implications about our climate research and so on. And this has a direct link with the payload which IUCAA is building called SUIT. And it has very different channels to look at the chromosphere of the sun, and including a calcium channel. And I'm very much interested to do my research continuation. So this is how, again, there are lots of smart students which I have, fortunately. In fact, the student who did this work, he comes from an engineering background, from an MTech PhD background, and now he has become one of the experts in this, and he got a very good postdoc in Boulder immediately after submission of the thesis. So point is, lots of mathematical tools, engineering skills, computational skills are necessary for modern day astronomy, and solar physics is no different. So this is, again, a classic example of how we are doing this automated, because nobody will have patience to look at things manually these days. Of course, our predecessors had this patience, which I don't have, to do things painstakingly by pencil, plotting it in the graph paper, projecting the image on a graph paper, and so on. But we have moved in a different modes of operation now. You can build the butterfly diagram also here, and as you can see here also, this 3D rendering of the butterfly diagram again shows you the very similar feature. What we have done is the area thresholding we have done. So the red ones are, again, the biggest plages, or the maximum sizes of the plages, and as you can see very clearly, they are restricted to the lower latitudes, whereas the blue guys, which are the smallest, they tend to go to very high latitude. So this calcium has also information about the weaker field much more than the sunspot. This is, again, a very new aspects we are getting, which sunspots do not provide us much, because the sunspots, they do migrate to the equator. They don't go to the polar thing. Only the diffuse field goes to the polar region, and the diffuse field can be mapped by the calcium images, not from anything else. So the calcium resources are actually more valuable now than the white light thing now. So there are, again, lots of work which we have done from calcium, generation of this Carrington map for 100 years. My idea is to make this data or not only public to the community, but also to generate some of the products which directly people can use it, or theoreticians can use it. In fact, after we published this paper, of course, now ABJ also insist that your data should be also available with this, with the published article. And what we have done in all these Carrington maps, they are there all as a part of the article itself. And in fact, I'm very happy to see that Carrington maps have been used by many, theoreticians across the globe now. So then we also try to do this connection of, as I mentioned, plages are formed in the calcium, which is 1500 kilometers above the solar surface. So how well they're connected. So we produced, a few articles on that. There is another aspect on the solar surface. Solar surface shows the manifestations of the convective cellular size on the surface, which are called granules. But when you go to higher layers, you see supergranules. So these are again direct manifestations of of the convection underneath the surface of the sun. And those parameters of the supergranulation size, their shapes, they also tend to vary with solar cycle, and that has a lot of linkages with the solar irradiance. Because as I mentioned, the solar irradiance has a lot more importance in our climate. And in fact, again, the suit payload has many different filters to look at this solar irradiance variability with long term. And I'm looking forward to that payload doing science with that as well. Then I come to the third data series, which is called the H-alpha. And H-alpha detects the filaments. And this is again a data archive. We see similar pattern that beyond 1980, there seems to be a drop in the data, in terms of the volume and the quality and so on and so forth. This is a comparison of the H-alpha archives across the globe. The green one is from the Kodaikanal. And if you see, this purple one is from Meadow in France. So this is the only probably two data sources which can compete. But interestingly, Meadow data is still not digitized. In fact, we had an IU symposium a couple of years back, and these people from across the globe, they came and they were impressed that we could do this digitization for this last 100 period, and they pushed their government to get some funding, and they have started the digitization process. Meadow data is there in the drawing form, but they don't have the images. I think arguably Kodaikanal is the only place where we are giving away the raw images and also different levels of the calibrated images to the entire community. No other places in the globe has such a long, consistent, data sets. So we could be, proud of that. This is how the filaments are detection. Again, it is very, briefly mentioned. There is some Otsu method which has been utilized for identifying these filaments and then producing, you can detect these filaments. You can look at their central latitude, then their longitude. Then the filaments are also tilted. As you pointed out that the sunspot pairs are also tilted, filaments also are often tilted. Not often, always tilted. So their tilt also provides information about this magnetic field location and orientation. And of course, the length also signifies something. The area also signifies something. So all these parameters we could generate this kind of butterfly diagram. And as you can see, I will point out few things. Here you see this poleward migration. This is not possible to do it from the white light or sunspot alone. This poleward migration has a lot of things linked with the meridional circulation and so on and so forth. This is a new field which has emerged. So my point is combining H-alpha, combining calcium and the magnetogram data over a period, where magnetogram or magnetic field informations are there, you train your data set, and then you go back to the history. That's how the AI works. So you can just get a hint that what we are trying, that over the period over which your training becomes very good, and that with that training you go back to the history and generate many more series. There is another data set, which is the fourth data set series in Kodaikanal, which depicts this kind of objects called prominences. Basically, these filaments are like, they're called sort of magnetic cloud floating in the atmosphere of the sun, in the chromosphere. When they're seen off limb, they appear as this in emission. So this is how the location of the prominences, but again, the location of the prominences provides a lot of information in terms of the magnetic cycle. So this is the data series. Again, you can see the data volume dropping beyond 1980s and so on and so forth. So we can produce this kind of butterfly diagram, and we produce these kind of poleward migration. So this is a very new result. And this poleward migration is a new result which a lot of dynamo theories are using. Now, as I pointed out, that it's just not the Kodaikanal alone. We are moving forward. We are collecting data from different observatories. We are trying to combine this, cross-calibrate it, and you can see when you do that, your results looks much better. So here the butterfly diagram with all these poleward migrations and so on and so forth really is valuable information. So this has appeared in the Art and Space Science a few months back, and I will probably move on. So the point is, there is a multi-wavelength aspect from the Kodaikanal archive. Full coverage of the sun. Sunspots provides direct information about the strong magnetic patch. Filaments also provide something called neutral lines. Essentially, filaments are known to be formed in the neutral lines across these two bipolar regions. So you can imagine, even if you do not have the magnetic field information, by knowing where the filaments are, it gives you an indication where the magnetic neutral lines are. So it really provides you additional information. Plages, as I mentioned, as seen from the calcium images, also show the weaker field. So by combining the sunspot, the strong field, and the plage information, you are getting a much more composite data set. And then, of course, the prominences which are forming off limb, and they are incubator for coronal mass ejections, as we know. I will not get into this. This is the big study which we are going to do with the Aditya mission. These are huge explosions of the solar atmosphere which ejects plasma blob in the interplanetary space. But now we understand prominences are the core of those different ejections. So if you can get a historical information about the prominences, that will also provide us a new data set. So again, combining the white light data, calcium data, and H-alpha data, it gives you a more composite series from one observatory alone. Now, of course, you can cross-calibrate your data with observatories across the globe, and then you can build your data sets. This is the point which I also would like to emphasize, that this digitized data archive was produced in collaboration with IUCAA. It was a very modern approach, and there is a team. I will Kaustuv and his colleagues, and Ajit was instrumental in pushing us and tying up these two groups to get this archive in the into the public media more efficiently. So they use a framework called Bootstrap to give a modern look and feel of the overall website, built on Python framework. This is again, a step forward from earlier Java, which we had. And there are lots of tools for animations and so on. So this is again a very good example that how different teams can combine their skills and make this kind of data available. And I'm looking forward for my next big data projects to work closely with the IUCAA team to do this. So this is a website. Please have a look at that. This is a unique opportunity for multi-wavelength study of the historical data. In the historical data, people were not looking at multi-wavelength aspect that much, but we know modern day astronomy can be only done if you look at it a multi-wavelength aspect, and solar physics is a very classical example. And this is a unique archive where such possibilities exist. So I have to acknowledge my gang. So this is my comparatively slightly older gang. This is called and popularly known as Dipu's gang. But of course, all of them were not working on digitization program at all. So Sudeep was my former student. He started doing coronal seismology, but ended up with doing this work. Although in his thesis, not a single paper is there from this, but he chose a first postdoc in Max Planck on the subject, which is not their part of his thesis. But I love this flexibility and openness. So Sudeep has gone to Germany about a year back. Shubhamoy did the work on calcium. Sudeep worked on the white light, and all these particles are have moved to different places. Tanmoy is in US. He was working on the space-based program. Vaibhav is in Belgium, and Nancy is in Norway. And these two are actually still remaining. Probably they're stuck to COVID as a postdoc with me. But I have a more younger gang, and that's the distribution of my younger gang as it stands. And some of the names are there. And thank you for your attention. And you see Kaustuv and other members who have been instrumental in building this archive as well, and making it available to the community.
Thank you very much. Thanks, Dipu. Can I turn on your video and see whether, if anybody has questions, please put up your hand. And you already are getting quite a lot of applauses. There is a question from Axel Brandberg. Please unmute and ask the question, please. I'm trying to unmute.
I'm Axel Brandberg. Nice presentation. I very much enjoyed it.
Axel, yeah.
At the time when you talked about the north-south asymmetry, you dropped out a little bit, so I may have missed a little bit about the connection with dynamo theory. But one of the things that we do expect as a potential explanation is that there's a competition between a dipolar and a quadrupolar mode.
Right.
And that would imply then that there's indeed an asymmetry in the magnetograms. And between north and south, there should be a different strength in the poloidal field that should be quantitatively measurable. My question then is whether you have tried to make any such connections in terms of the actual magnetic field strengths, whether that leads to an asymmetry that could be correlated with, for example, the sunspot area asymmetry. And then a connected question is related to the poleward branches that you see in the filaments, whether there is a similar asymmetry that may actually change over the cycle.
Yeah, very good point, Axel. So, of course, as you know, I've just put up this, magnetogram information. This is not from, this is a ground-based magnetic field information, the best what we have. Unfortunately, the polar field, strength is much weaker than the strong field, as you, definitely know.
Right.
So we do not have that precision to really make a distinction between 2 Gauss or 3 Gauss. What we have is only the information in terms of the polarity and these kind of surges. So I skipped details of this particular slide, but since you asked the question, I'm trying to get, so this, basically what you see is this, these are called the polar surges, and that you see also in terms of the magnetogram. So right now we can only talk about these surges, their timing and polarity. And here, actually, this particular surge, which has opposite polarity, is directly linked with the double peak behavior which we are talking about. So this paper which we did with Vidya Karak, there we indicated that these surges, which are of unusual nature, is responsible. And somehow this is again related with the rogue sunspots area, which also some people have termed, and so on and so forth, because you have also anti-Hale sunspot pairs often in some phase of the solar cycle. So there seems to have linked. But again, to coming back to your question, we do not have a very good quantitative measure about this polar field. And what we have is this rate. Somehow these gradients gives you also indication about the rate at which this poleward migration is. And that also clearly shows asymmetries in the 2 hemispheres. We have a paper under review, and that is done from the filaments as well, as you rightly indicated. So filaments does provide us this information, and this is under review. So hopefully we'll be able to show you the results very soon.
Okay, thanks very much indeed.
Great. So next we have Avinash Deshpande has his hand up. Go ahead.
Yeah, maybe this is a general question, and maybe you commented on it already. I might have missed. What is the origin of the 22-year cycle? I mean, how does it relate to the parameters of the star?
Okay. So what we understand for the dynamo theory, there are a few ingredients. One is, of course, the differential rotation and the convection. So it's an interplay between these two, which is responsible. But there are other parameters, as I indicated, is this diffusivity parameter which one chooses. And if you choose a different extreme, then you will get different kinds of strength and cycle length and so on. And the other important also is this meridional circulation, which is acting as a conveyor belt. So the point is that originally you start from a poloidal field, and because of the differential rotation, you get a toroidal field. and then the decay of this. There's something called the Babcock-Leighton process, which is invoked, which describes this diffusion of the active regions and the generation of the polar field, cancellation of the field, and that field drags back to the base of the convection zone. So all these different parameters essentially dictates the cycle length at the strength. And since it was trying to link with the other stars, so essentially what we understand is most of the solar-like stars also has a rotation, and depending on their age, how much their rotational speeds and the differential rotation patterns and all that again dictates the cycle length and so on and so forth. But obviously for that many stars, we still do not have the consistent data, but there are lots of stellar oscillation this cycle data is available now, and there are these kind of predictions. Again, there is also a direct link with the age and the stellar rotations and so on and so forth. The stars tend to slow down with the age. So all these parameters will be sort of responsible for the solar cycle or the stellar cycles parameters eventually.
Thanks, Dipankar.
Thanks, Sanjit. Go ahead. Sanjit, go ahead. Sanjit's next.
Yeah. Okay. Okay, you can hear me probably. Okay.
Yes.
So my question is actually about the public data. So in different communities, of course, we have to now make the data public. I'm just wondering how many people actually use the data. Like, since you have been doing it for a couple of years, I think there will be some idea if you have, especially in India.
Yeah, I must admit one thing, handling this kind of large data volumes and also, old data has a lot of challenges also in terms of, a lot of sophistication you have to actually invoke. So you need experience. So the people who are in the business, I would say that way, are using this data. This data is now available with the Germans. It is available with the Americans. It is available with the Russians and the Chinese. And I saw, last month there was a paper. 2 years back they were communicating with me and so on and so forth. I said, not necessary. You don't have to, collaborate with me for this. So they have a very detailed work on this particular, data from Kodaikanal, entirely from Kodaikanal. So now this distribution is happening across. But having said that, from India, I don't see that many people have been effectively been able to use it, because as I said, it needs a little bit of sophistication. I have good, bright students, they are using it, but I get inquiries and there are some people in IIT, they've done it, and some universities, they've taken the data. I've not seen any publications yet, but that's something which probably, time will sort of, prove.
Thanks very much. I mean, actually, so are you saying that, from outside India, the system, only one major group has so far used it? Or, I mean, in terms of publications, or there have been quite a few?
Yeah, no, there have been quite a few. Now this cross calibration is happening, but it takes time. Of course, in the Western world, the manpower is a big issue, and a lot of people are involved with newer projects. So the long-term study always gets a slightly, second-grade citizen, treatment, unfortunately. But there are quite a few people. But this particular area, there have been always, strong collaborative efforts because of the large volume of data and the skill set. Because unless you understand the data, sometimes, you will interpret it wrongly, or you will, record things wrongly. So sometimes it is important to. So we have tried our best to make a lot of documentation available in terms of the data calibrations, and we are probably the first time giving away the calibrated data series also, which has not been the case in the past.
Always a great thing about archived data. If you give away calibrated data, then you find people using it much more often.
That's correct.
KP Singh is next. He has his hand up.
Dipankar, nice talk. I want to know, is it possible to tell this cycle period for different stars, sun-like stars, let's say Proxima Centauri, based on any theoretical model?
Yeah, I must admit, I'm not an expert, and Axel is there. Probably Axel will know more about the stellar current data, what are the stars which has been recorded. So there has been quite a few, but as you can imagine, there are lots of data gaps. So the accuracy of these periodicity numbers and all that is always a big question, because you need the data to be spread over many years and so on.
Observationally, I'm saying theoretically, can one predict some cycle for?
Oh yes, that has been I mean, Axel has been doing that quite a lot actually for other stellar context. Yes, there are lots of work on that.
Okay.
Axel, would you like to comment on that?
Yeah.
I don't know whether it's there. I can unmute you.
Yes.
Yeah.
So I didn't hear everything that you were saying because I was filling up my coffee cup here. Yeah, so indeed, you mentioned the connection with the meridional circulation. And one of the arguments that emerges from comparing the stellar cycle data is that as the star rotates more rapidly, we know that the cycle frequency increases and increases more rapidly than the angular velocity increases. So the ratio even also increases. And that is something that is not reproduced by the corresponding change in the meridional circulation. And so one would then, from a Babcock-Leiten type dynamo that is based on meridional circulation, expect that the cycle period would behave the wrong way. And so I think that's potentially an important aspect which could potentially kill the Babcock-Leiten mechanism, if that's really confirmed.
Yeah, that's a criticism about the Babcock. But I just wanted to point out there is a science paper, I think a couple of weeks back in Science on this meridional circulation from the helioseismology results. They actually at least could say that it is a single cell, because that was also under debate for some time, that whether there is multiple cells and so on. So this is the paper which I noted a few.
Yes, this is an additional aspect with the multiple cells, and potentially not even such a crucial one, because as one of the people in this community pointed out, is what really matters according to the Babcock-Leiten is the meridional circulation at the bottom. So even if you had multiple cells, it is only the bottom one circulation which matters in that case.
Yeah, Arnav was to point out that, yes.
But even then, the sense of change as the star would rotate more rapidly would be the other way around. And so I think it is indeed important to make more explicit connections with stellar observations. It seems to me that this Babcock-Leiten dynamo would not work for any of the other stars. That's not to say that any of the other dynamo models really work very well. There is, I think, a major problem in terms of dynamo theory in general.
Thank you very much. Thanks for the contribution, Axel. Anybody else want to ask a question? Going, gone? Is nobody else? Okay, then let us thank the speaker again. It's wonderful. I mean, we can't really show our applause right now, but here is a Zoom applause that we can offer to Dipu and for a wonderful talk today. And thank you very much.